So this will be then on the topic of energy efficiency, which is, of course, very important in the context of neural circuits. And we heard several of those neural circuits yesterday, sessions on neuromorphic computing as well as on deep learning. Oh, I think I'm going up rather than going down, sorry. So there has been great excitement in the field of artificial intelligence. So just last year we had this amazing results of a machine beating the human. Right? This was then Google DeepMind versus Lee Sedol, the Go world champion, who was just defeated in a very emotionally embarrassing manner here, as you see on the right. But what's really going on here? A few points to be made here. So first of all, this is not old school AI. This was actually neural circuits, deep learning neural networks at play. That's one observation. And the other observation here is that the comparison is not quite as fair as you would want it to be, right? So sure, this was deep learning, but it also was DeepMind using basically Google's deep pockets, right, of almost infinite resources in data and power here. As you see, basically 100 kilowatts versus then about 100 watts being very generous here in the power. It's more like I said 10 watts or 15 watts of power in the brain. So clearly you can do much better here in terms of energy efficiency. And that's what motivated actually 30 years ago or 25 years ago neuromorphic engineering. And it's important to go into this not just from a cognitive level in terms of performance, which was pursued by AI, but also looking at deeper physical foundations, which are there as well, right? So taking inspiration from biology not only in the function, but also in the structure and organization, which they can also inherit then its great, the great energy efficiency of computing in the brain, as well as its great resilience to operate under noise, imprecision, with environment and uncertainty. Right, so about 30 years ago, the field of neuromorphic engineering was actually started as a synergy at the very physical, foundational physical manner by Richard Feynman, who told us, in fact, there's also a lot of room at the bottom. And that started really because the field of nanotechnology and the events we're noticing here today. And also Carver Mead, right, who helped then also launch the field of digital systems synthesis, right, which really was pushing then integrated circuits towards a system perspective that allowed them all the advances in information technology. But those two also, just lesser known, at the same time, advocated the principle of analysis by synthesis, in which, as if you look at what Richard Feynman was telling us, this was actually his blackboard just the day before he died. Right? So what I cannot create, I do not understand. So in order to understand really what's going on in the brain, you actually need to be able to synthesize brains. And Carver Mead took this to heart and actually started this field of neuromorphic engineering, basically building artificial brains in silicon. And to understand this endeavor here, so indeed we have this analysis and synthesis that go together. Analysis is basically neuroscience, synthesis engineering, and this has to happen at all different scales in representation, right? So you have, because at the bottom layer, you have the physics all the way from ion transport through ion channels, which has physical isomorphisms in then transistors operating in subthreshold. In fact, the steep slope that we're discussing at this meeting, right, has also analogies of Boltzmann physics with ion channels, but there the slopes are much steeper that we're discussing today and yesterday. Slopes in the order of a few millivolts per decade, achieved through correlated ion transport. There's something to be learned there as well. And then the higher layers, you also have physical isomorphisms then of Boltzmann machines and learning that can also be harnessed for building machines that are intelligent. So here's also important to note that some of this massively parallel computing, distributed computing, that now today is referred to as non-von Neumann computing, is actually very unfair to von Neumann, who actually 50 years ago started this field, started looking into how the brain is organized in this parallel computation. And I guess still 50 years later, we're still doing mostly serial or sequential computing and having this discrepancy between memory and compute operations. There's something to be learned here, right? So, in order to quantify efficiency, going towards extremely efficient learning machines, it's important, of course, to look not just at the energy, but also at what is being done by the energy. And then here we consider task complexity, right? On a log scale. The vertical axis here is then the machine complexity, right, which translates to power and other metrics. And you can think of this vertical axis as basically Moore's law, where each, right, because we have had a logarithmic increase an exponential increase in density. So on the log scale is basically a linear climbing up of this ladder. And now we're reaching a limit here. We can't go any further, given the physical limits. The assumption all the way along with Moore's law has been that in order to get better performance, we just scale things up. And it has been great, but clearly more can be done by reorganizing the computation in different matters. And this is now is really driving the latest advances in deep learning and machine intelligence, in which what used to be a linear trade-off between machine complexity and task complexity with digital search and exact methods for computing are now being replaced with more collective analog computation, non-von Neumann computing that is inspired by basically the approximate reasoning that this happens, that takes place in how the brain is organized. Right? And so it's important to look at the energy per task. So basically, this can be decomposed in energy per operation, which can be optimized through engineering, but also operations per task. Right? We can minimize the amount of computation to be done in the first place, and that will also then bring down your overall energy, right, for improvement in efficiency. Right, and so there you can get, so in the neuromorphic engineering effort, right, you can get down to energy levels of about a femtojoule per synaptic operation. So here we have massive power operations. So the synaptic operation is the key metric here, so energy per synaptic operation. And then at the same time, by deep learning and also adapting deep learning approaches to the physics of the medium, you can also then further improve, basically have fewer operations for doing a given task, for instance here for the digit classification. So it's important to have the synergy of then neuromorphic engineering and deep learning, both hardware developments at device level and circuits level, and then algorithmic advances in learning and computer science for this to happen. Right? And so indeed, we have these different disciplines, in fact, also represented here at the meeting yesterday, right? Where definitely advances in nanotechnology are extremely important towards the densities that are necessary for reaching a level of complexity of say, the human brain. But at the same time, also then it's important to have this deep learning and other approaches, right, to abstract the complexity of the environment into a representation that, even though it seems daunting of having 10 to the 15 synapses that you need to have on this chip to get close to human cognitive performance, still you need to be able to abstract the complexity of the world into those Oh, there it is. There we go. I see. Okay, so here's a comparison of then recent large-scale neuromorphic devices. And so we go here for cognitive performance. So we're looking at large scale, right, where deep learning can be used for then training those machines. And most of those are actually doing inference and not learning. So basically learning is then done off chip. And then once the system is trained, then the weights are then projected because on those chips. So we have some digital chips. So the ones on the left, the two ones on the left here. Sorry. The two ones on the left here are digital chips. So you have Spinnaker, developed at Manchester. Then here you have IBM True North, which is an asynchronous digital chip. And then you have 3 analog chips on the right here. It's the Heidelberg facet brain scale chip. So both this facet brain scale chip and Spinnaker, those were developed through the Human Brain Project. Synapse, IBM, so IBM chip was developed through the DARPA Synapse program. We also have the Stanford Neurogrid chip developed by Guanon here, I guess, recently. And here's a chip developed at UCSD, right, where we had also similar performance. So the key here is that you can look at size and complexity. The bottom line is energy efficiency, joules per synaptic events, and now all the systems are approaching more or less energy efficiencies in the order of a few tens of picojoule per synaptic event. And so that's great, but yet most of those are limited then still by memory access. Right? And for making further advances, and then it's important to have better matching between this processing power that you have in this for neuromorphic computing, but then also the memory capacity and the interface, because of bandwidth. Right. Here's another way of looking at this. Right? It's important for this to scale, to have both flexibility in how you can reconfigure the network with 10 to the 15 synapses. Clearly in our brain we have 10 to the 12 neurons. Not every neuron is connected to every other neuron. That would be 10 to the 24 synapses. So we have sparsity in the connectivity. So and even though most of those connections are local, in the direct neighborhood, there's still a significant fraction of neurons that will fan out and making connections all the way to the other side of the brain. So long-range connectivity is extremely important. But still you want to have the capability of each neuron to connect to, in principle, every other neuron, right? So combination of expandability, so scalability and efficiency in how you can reach long range, as well as flexibility in which each neuron can connect to other neuron, are both important. And typically has been this trade-off between the two, but so now there are systems, Spinnaker and then also higher, the system we developed, in which by using a hierarchical representation, right, basically small world, networks, because hierarchical representations in trees, combined then with arbitrary connectivity, can give you then flexible and yet expandable connectivity in neuromorphic computing. And that's extremely important for scaling up the systems, right? So here's an example of what we call IFAT. Higher stands here for hierarchical address event representation. And IFAT stands for integrated and fire array transceivers. So the principle here is that when a neuron fires, it connects to other neurons, to synapses, right? And the way this can be done efficiently is by going into tables, memory, or you define the connectivity, because in basically virtual fashion. So this allows you to dynamically reconfigure your network very easily. And then you have those integrated fire array transceivers, right, that are with addressable neurons. Right, so you have synaptic inputs addressed coming in, and then when neuron fires, it requests an address, an event coming out with the address of the neuron. And so this way you can construct, in principle, arbitrary neural networks. To scale this up, you need to have this hierarchical means for partitioning your network, where you have mostly local connectivity, and then you have this global connectivity taken care of by routing basically events, neural events, through the hierarchy. Right, so you have these local elements with integrated fire array transceivers with local memory defining these connections. And then you have a network, because here is a board. You can have a rack of those boards, and then you can have a supercomputer center, and then multiple sensors can be combined together over the internet for building very large networks, right, as a scalable thing. So this operates at about 22 picojoules per synaptic event, which is perhaps great, but not the best we can do. And the bottleneck here is really then the memory bandwidth. So in order to do better than that, we need to have means for directly connecting those neural processors to memory elements. And those resistive memory technologies, such as PCM, so phase memory, as well as resistive RAM, and other ones you have heard about today, yesterday, are great because not only they're good for non-volatile storage, but they also are implementing inherently a synapse, a conductive-based synapse. Because what is a synapse, after all, in the brain? You have a presynaptic neuron action potential that activates this conductance between the reverse potential and the postsynaptic membrane. And then you have those currents, those conductances that couple, and so this current basically sum in the soma for giving rise then to the action potential on the postsynaptic side. So each element can be seen as directly a synapse that is activated by presynaptic action potential. Right? So you can have spike-based computation that can take advantage of the same elements rather than having to use this as a digital memory. So you can have a full in-memory compute capability where each memory element is actually a full computation element, multiply cumulative. Right, so at Stanford, Philip Wang's group developed those amazing technologies then for actually also training those crossbar arrays with those phase change memory and also ReRAM technologies, right? For implementing synapse arrays, right, that adapt based on what is called spike time independent plasticity. Is a biological rule that tells you, right, how a network will adapt itself. It will change the weights according to activity that is spike-based, just based on timing, relative timing of spikes. Right? And so now we're actually taking this technology and putting it on top of CMOS, where then in CMOS we actually have the neurons implementing those integrated fire array transceivers, which can also be addressed for long-range connectivity. And then locally have this highly dense, efficient local connectivity of basically synapses on top of this PCM or RM synapses on top of your CMOS. Right? So that's about technology, and in this way we think we can go down to femtojoules of synaptic operations. But again, so I mentioned it's extremely important also to look at the algorithmic side of things. And so here we also looked at Boltzmann machines and how to officially implement them for neuromorphic computing. And you heard about Boltzmann machines yesterday as a means for doing stochastic neural computation in a massively parallel system that exploits the inherent stochasticity medium to solve very hard problems that otherwise cannot be done with deterministic schemes. So here in a Boltzmann machine, you have noise as an additive mechanism. So so the brain actually has plenty of noise that is available there for free at the synapse level. In fact, our synapses in the brain fail about 50% of the time. Right? So a presynaptic action potential doesn't actually reach, right, the postsynaptic site with, right, due to many factors, the release of neurotransmitter and also binding on the postsynaptic site. So those are stochastic processes that fail about 50% of the time, and yet we're doing so great in neural computation. So the reason why I think is because that stochasticity can be harnessed. It's a great thing. And so we actually harness this stochasticity and basically having those synaptic connections being stochastic as a multiplicative rather than an additive noise mechanism that actually performs better than Boltzmann machines in doing inference and learning, where the learning is then implemented using an online unsupervised form of contrasted divergence, which is the learning algorithm used for Boltzmann machines, based on the same spike time dependent plasticity. It can be implemented with this RM technologies. Right? And RM is also great for stochasticity. RM and PCRM are great for stochasticity. And doing this, actually, we get faster convergence, fewer operations than a digital Boltzmann machine that's implemented, right, on a digital machine. So fewer operations, fewer synaptic operations than the multiply cumulus that you need in a digital machine emulating the Boltzmann machine. Yesterday, we also had a question, so what are now the limits of energy efficiency, and how does and why would we want to go on the edge? Right? So what I presented so far as a means actually that doesn't have to go off the edge. You can have farms of those general purpose machines for doing very large problems, such as what DeepMind has been doing. And so there's a way forward there for tackling very hard problems. But you can also ask yourself, can we have also more efficient means, right, because at extremely low power, interfacing, say, with sensors. And yes, you can. So you can even get great advances. If you know exactly what algorithm you're doing, you can implement this in hardware. And so here are examples of where you have sensors coupling then to systems that we can think of as smart ADDs, smart analog digital converters, because you do some analog signal processing, and then out comes a digital answer, right, that actually has more information about your problem than you would be getting just by ADD conversion. Here's an example of what we call the Kerneltron, which was developed, I guess now 10 years ago, or more than 10 years ago, as an adiabatic support vector machine on silicon. Right? Support vector machines are other learning machines, right, that are based on advances in statistical learning theory. Basically, you can think of those as massively parallel template matching processors. And so here we have an array of elements, charge domain elements that are both doing storage of a template element and also then doing the compute by basically capacitive coupling. And by recovering charge in the process, right, rather than wasting it, so recovering it in a non-destructive manner as a capacitive readout, and also then combined with some adiabatic techniques for recovering also the charge for driving the lines, right, with inputs, right, we're able to get about a teramax per milliwatt, which is basically femtojoule of better than a femtojoule of operation per synaptic operation. And this still had been, I guess, a record. This was 10 years ago. Now, the latest machine learning systems or inference machines are getting at that level, but now, today, those are using deep submicron technologies at the 20 or below nanometer node. This was basically 250 nanometer, basically 0.25 micron technology. Right, so the principle here was basically using resonance in adiabatic coupling between external tank and internally to the chip you have your capacitive, I guess, load implied by your charge domain computing elements. And at resonance, basically, if you make sure that the activity is about balanced, that it goes halfway with stochastic computing, you can hit it nicely where you actually recover most of the energy. And that's how you're able to do this. Another system, how many minutes do we have? I think I'll wrap up here, yes. Right, so, and you can also take this to another extreme, right, where if you have now multiple, let's say you have an array of antennas, right, right, you can do the single, so you can do the signal processing here, for instance, for doing adaptive beam forming, right, at an effective 14-bit of resolution, right, basically dynamic range of 90 dB. And this way you can bypass the needs for high resolution ADD conversion, and you can drastically reduce the power, not just the power, right? So if you were to go to an ADC directly and then have a DSP for doing the computation, your path will be dominated by the ADC. So now you do some analog processing for doing this beam forming, and then you can dramatically relax the power here, and the power of this analog signal processing is actually still quite good. In this case, it was basically 2 picojoule per multiplied cumulate in the analog domain using charge domain computing. So definitely with dedicated architectures, you can do very well energy efficiency, but even also in this general purpose computing, you can do quite well as well. And so I think there's a path forward towards femtojoule level computing, general purpose computing with neuromorphic devices. I'll finish there.
Very, very interesting. You mentioned 3 recent machines that were analog, and I'm just wondering, were they all based on crossbar arrays? I'm referring to the Brainscale S machine, the Stanford Neurogrid, and the UCSD IFAT. Are they all?
None of them are. No. So
none of them are cross. So in what sense are they analog?
Well, they're analog because the circuits used for implementing the neural dynamics use transistors, right, for conductances, use capacitors for integrating the values, right? But the memory storage is still mostly off-chip. Some of those have actually on-chip storage, but this was limited to some capacitor on I guess, right? And we're still waiting to see neuromorphic computing at scale. They'll be using RM or PCRM elements, and this is a work in progress. So Philip and I actually work in this area, and there's other groups too. But so we're still waiting to see this very large scale integrated memristor elements to really make an impact on neuromorphic engineering. But hold on, it will be in the near future.
So I have a question about this stochasticity. So the results that you showed are fantastic, that the stochasticity actually makes it more efficient. But what is the physical insight behind it? Why does it make it so efficient?
So you're referring to the Kerneltron, right? Right. So, well, basically, you have an array of those compute elements, right? And so you're transferring the charge, the output, when your input is a 1, you don't transfer it when the input is a 0. So then the charge coupling that you have, or the capacitive load that you have in your computation depends on the data. So if you can somehow modulate your data, right? Basically as a delta sigma modulator, if you can modulate or noise shape your data, right, then you can assure that on average you have the same number of elements that you're actively driving, and then you can ensure that this capacitance that you have, your capacitive load is constant, and then you can tune your system at resonance. Right? This is an example where tuning a system at resonance by modulating the computation was able to get there. But there probably there may be other good reasons for using stochasticity computation, stochastic resonance, for instance. Right?
Okay, are there any other